All right, welcome to your very own deep dive. This time, we're going to be tackling recurrence equations.
Oh yeah, recurrence equations.
These are the mathematical expressions that we see all the time when we analyze algorithms, like merge sort, binary search.
Yeah, you see them everywhere.
And it can be a little intimidating, but
Yeah.
once you understand them, you can feel like a coding wizard because they let you predict how an algorithm will behave even before you actually run it.
Sure.
So we're going to be unpacking all of this based on a really cool university lecture that we found on data structures and algorithms.
A classic topic. It's going to be good.
Okay. I am ready to unlock my inner coding wizard. But before we actually get into solving these equations, I think we need a quick refresher on recursion itself. It's been a while since my computer science classes.
Yeah.
Like, what even is recursion again?
Yeah, so recursion, it's kind of like when you hold a mirror up to another mirror.
Right.
And you get that like infinite reflection, right? So it's basically a process that calls itself within its own definition. Algorithms can be recursive too, and they call themselves repeatedly to break a problem down into smaller, like self-similar pieces.
Gotcha. So each time that the algorithm is calling itself, it's like another reflection in that infinite mirror tunnel.
That's a great way to think about it.
Okay, cool. But how do these reflections connect to recurrence equations?
So each of those reflections or recursive calls, you can think about it as a unit of work that the algorithm has to do. And recurrence equations, that's how we describe how that work grows or shrinks as the algorithm keeps calling itself, as it gets deeper and deeper into that recursion.
Okay, I'm starting to get it. But these lecture notes immediately jump right into this thing called asymptotic notation and use all these symbols, big O, omega, and theta. To be honest, I find them all really confusing.
Yeah, that's understandable. Asymptotic notation can be a little abstract, but it's really just a way of comparing how different functions grow as the input gets really, really large. Think of it like comparing two cars accelerating on a highway. One might zoom ahead while the other lags behind.
Gotcha. So instead of cars, we're comparing how quickly the work done by an algorithm grows as the input data gets bigger.
Exactly. And that's what big O notation is all about.
Right.
It describes that upper bound of an algorithm's growth rate. It's like saying this car won't go any faster than this. Omega notation, on the other hand, is kind of the opposite. It gives you that lower bound, like this car won't go any slower than this.
Okay.
And then theta notation is that sweet spot where it tells us that the growth is tightly bounded both above and below.
Okay, so it's like setting speed limits for our algorithms.
Yeah, that's a good way to put it.
Okay, that makes a lot more sense. But I have to ask, why should I, or really anyone, actually care about all this notation, all these equations? Is this just theoretical stuff, or does this actually have value in the real world?
Oh, no, it's incredibly practical. Let's say, you're building a website and you have two algorithms to search through a database.
Okay.
One might take hours to actually find what you're looking for. The other might take just milliseconds. So understanding how the efficiency of an algorithm changes as the data grows is really crucial for making those smart choices as a programmer. You don't want to be waiting hours for your website to load.
Right, efficiency is key, especially when you're dealing with huge amounts of data. No one wants to wait hours for anything these days. So how do we actually go about solving these recurrence equations? I'm looking at these lecture notes, and there are several techniques mentioned. Where do we even begin?
So think about it this way. It's like you have this toolbox, right? And it's full of tools. We have the substitution method, the iteration method, the Master Theorem, and we even have some techniques for dealing with these things called linear recurrences. Each tool has its strengths, its own place, and it's suitable for different types of problems.
So it's all about choosing the right tool for the job. Let's start with the substitution method. What's that all about?
Yeah, so the substitution method is a little bit like solving a puzzle, okay? You start by making an educated guess about the solution to the recurrence equation. Then we use some clever substitutions to try to prove or maybe disprove that guess that we started off with.
Okay.
It's similar to what's called a proof by induction. I don't know if you remember that.
Oh, yeah.
Where you start with this base case, and then you show that if it holds true, it's going to hold true for all the following cases. And the lecture notes, they use selection sort as a good example of this.
Selection sort, yeah. I remember that. That's the sorting algorithm where you basically keep finding the minimum element and then you swap it into place.
Exactly. And the recurrence relation for selection sort captures how the number of comparisons grows as the list gets longer.
Okay.
And we can use the substitution method to actually prove our guess for that solution, like showing that the number of comparisons, it's going to grow proportionally to the square of the input size.
Okay. I'm starting to see the power of this.
Mm-hmm.
We can actually prove how an algorithm's behavior scales with the input size. This is way more than just blindly running some code and hoping for the best.
Exactly. This gives you real insight.
What about the next tool in our toolbox? What's this iteration method all about?
All right, so with the iteration method, things get a little more visual. We're actually going to unroll the recursion like a tree. Each level of that tree represents a step in the algorithm.
Okay.
And this helps us see, like visually, how the work kind of expands and contracts with each recursive call.
So we're basically drawing out the family tree for the algorithm.
That's a great way to think about it, yeah. And one example that the lecture notes use is binary search, which I think a lot of people are familiar with. That's that divide and conquer strategy for finding something specific in a sorted list, right?
Like guessing a number between 1 and 100, and each time you guess, you're told higher or lower. So you're eliminating half of the possibilities with each step.
Yeah, exactly. And when we visualize that with this recursion tree, we can see how quickly the search space shrinks with each recursive call. That really helps us understand why binary search is so efficient.
Ah, I see. So the iteration method gives us a really nice visual way to understand exactly how the algorithm is working step by step. What about this master theorem that I keep seeing pop up? It sounds pretty intimidating,
Oh, it does sound pretty intimidating.
like something from Star Wars.
Yeah, the Master Theorem. It sounds like some kind of like final boss battle, but it's actually a really powerful tool that can solve a specific type of recurrence equation quickly and efficiently. Basically, it analyzes the recursion tree's growth, and it just gives us the shortcut to get to the solution.
So it's like a cheat sheet for a particularly hard type of problem.
Yeah, you could say that. But there's a catch. It only works for recurrence equations that fit a very specific format. So it's important to recognize when you can use the Master Theorem and when you have to rely on some of these other techniques.
Right. Just like any powerful tool, it has its limitations. Knowing when not to use it is just as important as knowing when you can use it.
Exactly. And, the lecture notes actually warn us about some of these potential pitfalls, like, trying to use the Master Theorem when the recurrence equation just isn't in the correct form.
Oh, so we need to make sure that we're not falling into any traps. We can't just blindly apply formulas. We really need to understand the underlying concept.
That's the key.
Okay, so we've covered a lot of ground so far. Everything from the basics of recursion to some really powerful techniques for solving these recurrence equations. I'm starting to feel like I can actually tackle these things, but we still have more to explore, right?
We do. And things are going to get a little bit more abstract as we kind of delve into the world of linear recurrences.
Oh.
This is where we really start to see some fascinating patterns emerge. Okay, so let's jump into these linear recurrences.
Yeah, let's do it.
The Master Theorem that was great for like those well-behaved recurrence equations,
Yeah.
the ones that fit that nice specific pattern. But what about the ones that are a little bit more unruly? That's where these linear recurrences really come in. They can describe a much, much broader set of patterns, but they also require kind of a different set of tools. So we need to expand our toolbox a little bit.
Okay, I'm intrigued. What makes them so unruly?
Well, think about a simple savings account, right?
Okay.
Let's say you put in like $100 and it earns 5% interest every year. The balance in your account after each year, you can actually describe that using a recurrence relation.
Okay.
This year's balance is just equal to last year's balance plus, that 5% interest on last year's balance.
Right, so the current balance depends on the previous balance.
Right.
It sounds kind of like that recursive idea we were talking about earlier.
Exactly. That's the heart of a linear recurrence relation. The current value depends on this linear combination of previous values. In the savings account example, it's just one previous value, but it can get more complicated, like what if the current value depends on two or even more previous values?
Okay, so our savings account, that's like a very simple linear recurrence.
Yeah.
What about like a more complex one?
Well, think about the Fibonacci sequence, that classic one, 1, 1, 2, 3, 5, 8.
Yeah, I've heard of that.
Each number is the sum of the two preceding numbers, right? So we can express that as a linear recurrence relation. The nth Fibonacci number is the sum of the nth and the n2 Fibonacci numbers.
Ah, I see. So in that case, the current value depends on two previous values. Makes sense. But the lecture notes, they start talking about these things called characteristic polynomials. And to be honest, my memory of polynomials in general is a little hazy.
Yeah.
What's the connection here?
So characteristic polynomials are this really clever trick we use to solve these linear recurrences. It's almost like you're translating from one language to another, from like the language of recursion to the language of algebra.
Okay, I like that. Walk me through that translation. How do we take a recurrence relation and turn it into a polynomial?
Sure. Let's take an easy example, like a homogeneous recurrence.
Okay.
Something like Tn equals 2Tn1.
Hmm.
So this is saying that the nth term is twice the n1th term. And now, the trick is, we're going to guess a solution.
Okay.
A solution of the form Tn, where is just some constant. So we're kind of assuming that the solution follows some exponential pattern.
So we're basically saying, hey, let's just assume that the solution looks like this exponential function.
Exactly. And then we just plug our guess into our recurrence relation, 2en(n-1) where we can simplify that down and we get c and 2. So our guess, it was correct,
Okay.
if en is 2. So a solution to our recurrence relation is Ten equals 2n.
Okay. That seems surprisingly straightforward. We just guessed a solution, plugged it in, and then boom, we got a value for nu. But what about more complex cases? What if the recurrence relation has, like, more terms?
Yeah, the process is similar. You plug in your guess, you simplify it down, and then you'll end up with this polynomial equation in terms of nu. And that's our characteristic polynomial. The roots of that polynomial, those are the values of nu that make the polynomial equal to 0.
Okay.
And those become the building blocks for the general solution to the recurrence relation.
So finding the roots of that polynomial is like finding the key to unlock the solution to the whole recurrence relation.
Exactly. Now, there are a few nuances here, like what happens if the characteristic polynomial has repeated roots?
Okay.
That's where the idea of multiplicity comes in. You might remember that from algebra.
Multiplicity.
Yeah.
That does sound familiar. I might need like a quick refresher, though.
Yeah, so multiplicity just means how many times a particular root appears when you factor a polynomial. So like the polynomial by 2, that has a root of 2 with a multiplicity of 2 because it appears twice.
Okay.
And for our recurrence relation solutions, a root with a multiplicity greater than 1, that's going to add extra terms to our general solution. So instead of just having terms like a, we also get terms like an and an2 and so on.
So the repeated roots add more complexity, more layers to the solution.
That's a great way to put it. It's kind of like adding harmonics to a musical note, you know? It just creates a richer, more complex sound. And you know what? A classic example of a linear recurrence relation with a repeated root is the Fibonacci sequence.
Oh, right, where each number is the sum of the two previous numbers.
Exactly. Its characteristic polynomial has a repeated root, which leads to that very distinctive pattern of exponential growth.
Okay, this is all fascinating. But we've been talking mostly about these homogeneous linear recurrences. What about these non-homogeneous ones? How do we deal with that extra term that gets thrown into the mix?
That's a great question. There are actually a few techniques for tackling those non-homogeneous ones. One common way is to try to transform the non-homogeneous equation into a homogeneous one.
Oh.
And we do that using some, clever subtraction.
Sure.
We try to cancel out that troublesome term that doesn't depend on previous values. And you know what? A really classic example of this is the Towers of Hanoi problem. I don't know if you've heard of it.
Oh, yeah, the one with the rings and the pegs.
Exactly. It's actually represented by a non-homogeneous linear recurrence. And by using this transformation technique, we can actually solve it and find the minimum number of moves required to solve the whole puzzle.
Wow. Recurrence relations solving ancient puzzles. I'm really starting to see how powerful these mathematical tools can be. We've covered a ton. Substitution, iteration, the Master Theorem, linear recurrences, it's a lot. But honestly, I'm feeling way more confident about tackling these equations now.
That's great to hear. And remember, it's not about memorizing a bunch of formulas. It's about understanding those core concepts, those strategies. Think of it like being a detective,
Yeah.
You use your tools and your reasoning skills to crack the case of the recurrence relation.
Ooh, I love that. We're like code-breaking detectives, deciphering the secrets of algorithms. But before we get too carried away with our detective work, I think we need to take a little break. We'll wrap things up and talk about some of the broader implications of all this when we get back. Don't go anywhere. Welcome back to our deep dive into recurrence equations. We've really covered a lot of ground, from the basics of recursion all the way to some pretty advanced techniques for solving those mathematical expressions.
Yeah, it's been quite a journey, hasn't it?
It has.
We explored the substitution method, the iteration method, that Master Theorem. We even went into the world of linear recurrences with those characteristic polynomials and repeated roots. It's like we've built up a whole toolkit now for analyzing how efficient algorithms are.
I'm definitely feeling a lot more confident about how to approach these equations now, but I'm also realizing that there isn't like one solution that fits all these problems, right?
Right.
The lecture notes really emphasize that sometimes we need to be more creative, more adaptable in our problem solving. What are some of those out-of-the-box techniques that we might need to pull out?
Yeah, that's a great point. Just like a skilled, craftsman uses different tools for different tasks, we need to be flexible in how we approach solving these recurrence equations. Sometimes the master theorem just won't apply,
Right.
or the problem is just presented in a way that we're not used to.
So we need to be ready to improvise.
Little bit, yeah.
What are some examples of those types of situations?
Well, sometimes we can make some progress just by focusing on finding the upper and lower bounds for the solution instead of trying to get the exact answer right away. It's kind of like narrowing down the possibilities. You get like a rough estimate first before you jump into all those little tiny details.
So we're setting some boundaries for our solution, almost like drawing a fence around it.
Yeah, exactly. And a good rule of thumb to keep in mind: logarithmic terms grow way, way slower than polynomial terms.
Yeah.
And that can really help us make a good guess about what that solution will look like.
Okay, so if we see a logarithmic term popping up in the recurrence relation, we know that our solution isn't going to be some crazy exponential function. It's a good sanity check.
Exactly, exactly. And another trick is to use a change of variables.
Okay.
Sometimes if you make a clever substitution, it can actually transform a really tricky recurrence into one that's much, much easier to work with.
Okay.
For instance, there's an example in the lecture notes where they actually replace a logarithmic term with a new variable. And that makes the whole equation way easier to solve.
So it's like shifting our perspective, looking at it from a different angle.
Exactly. Sometimes a fresh perspective is all you need.
Yeah, sometimes you need to shake things up a bit.
Right. And, speaking of different perspectives, there's also a technique for working with recurrences that just aren't in that standard form that the master theorem needs.
Right. The cases where the Master Theorem is like, nope, not my problem.
Exactly. In those cases, we might be able to find those upper and lower bounds by comparing the recurrence to one that's similar that we can solve with the master theorem. It's like finding a relative of the problem, but one that's a little easier to deal with.
We're borrowing solutions from our mathematical family.
Uh-huh.
I really love how creative we can be with these techniques. It's not just about blindly applying formulas. It's about understanding what's really going on and, being a little resourceful.
Yeah. Solving these recurrences, it's a lot like solving puzzles. It takes logical thinking, pattern recognition, and just being willing to try different things until something works.
This deep dive has honestly been such a fantastic journey into the world of recurrence equations. We've learned how to understand their language, we've kind of unraveled all those mysteries, and we've even seen how powerful they really are.
And, maybe the most important takeaway is that there isn't one right way to approach all these problems.
No.
It's all about adapting, being creative, being persistent, kind of like coding itself.
Oh yeah, absolutely.
Yeah.
Trying to solve these equations, it's a good reminder that problem solving, in general, is a skill that you can develop.
Yeah.
It just takes practice and, the willingness to think outside the box a little bit.
I couldn't agree more. And as you continue on your coding journey, as you start to encounter more complex algorithms and data structures, this ability to analyze their efficiency using these recurrence equations, it's going to become even more valuable. It's going to be a skill that you'll use all the time.
Great point. So to our listener, we really encourage you to embrace the complexity, even the beauty of these recurrence equations. They're more than just these math expressions. They're really gateways to understanding how elegant and efficient the algorithms that power our world are.
And remember, even when you're faced with like a really challenging equation, don't give up. There's always a solution out there just waiting to be discovered. Keep exploring, keep asking questions, and just keep pushing the boundaries of what you understand.
I love that. And on that note, we're going to leave you with one final thought. The lecture notes mention this really cool connection between recurrence equations and fractals. Those amazing patterns that repeat themselves at all those different scales. I wonder how deep that connection goes. What can these equations teach us about, like, the nature of complexity and self-similarity in the universe? That's something for you to think about. Until next time, happy coding.